Hello everyone, myself Aishwarya R. Today I am going to discuss about the most interesting topic in computer graphics and visualization. Now let us see what are the topics I will be discussing in this video. First one, two-dimensional pipeline. Second one, three-dimensional pipeline. Third one, RGB color model. Fourth one, CMY color model. Now let us see two-dimensional pipeline. Before going to the two-dimensional pipeline, we must know what are pipelines. Pipelines are the represent the conceptual models where the interaction and the flow of data for all the functions, where we can create an applications and we can save, modify, draw and display the pictures. Two-dimensional pipeline. This is a simple 2D drawing pipeline where it consisting of object word coordinates clipping where we can clip an elements by applying the word window. Then it has sent to the object subset. Then next a window to the viewport mapping. From window to the viewport mapping it has been sent to the object screen coordinates. Then object screen coordinates it rasterizes the images, rasterization takes place, and finally the display object will be represented. Two-dimensional pipeline. Basically, a two-dimensional viewing transformation pipeline refers to the series of steps where it involves in transforming and projecting a two-dimensional scene onto the two-dimensional viewing plane. These pipelines consisting of several stages that manipulate the coordinates of the objects in the scene to align them with the viewing plane. Now let us see what are the main stages in the two-dimensional viewing transformation pipeline. The main stages in two-dimensional viewing transformation pipeline are first one modeling transformation where we can modify the images, viewing transformation we can view it in the two-dimensional pipeline, clipping where the images has been clipped, only the required images will be modified, the projection, fourth one is projection, fifth one is viewport mapping. Now let us see in detail about two-dimensional pipeline. First one, modeling transformation. This stage involves applying the transformation to the objects in the scene to position them in desired location and orientation. These transformation may include the translation, rotation, scaling and shearing operation. The modeling transformation ensures that the objects are in the correct position relative to each other. Second one, weaving transformation. In this stage, the scene is transformed from word coordinate to the view coordinates. The view transformation defines the position and the orientation of the virtual camera or observer in the scene. It involves specifying the camera's position, target point, and up to vector, which determine the viewpoint, and viewing direction. The viewing transformation adjusts the coordinates of the objects to align them with the camera perspective. Third one, clipping. Clipping it is a process of removing any parts of the objects that fall outside the view frustum, which defines the position of the scene that is visible from the camera's viewport. The view frustum is typically defined by specifying the near and far clipping planes, as well as left, right, top, and bottom planes, where the objects outside these frustums are clipped or discarded from the scene to improve the performance and eliminate the unnecessary calculations. Fourth one, projection. In the projection transformation stage, in two-dimensional pipeline, object is projected on the screen, where it involves converting the two-dimensional coordinates of the object to screen coordinates. Common types of projection used in two-dimensional graphics includes orthographic projection and perspective projection. Fifth one, viewport mapping. After the model transformation, the next step is to map the transformed object onto the viewport, which represents the area of the screen where the object will be rendered. The viewport defines the size and the position of the 2D scene that will be displayed on the screen. Now let us see three-dimensional pipeline. Three-dimensional pipeline where we need to choose a viewing port position corresponding to where we would place a camera. Viewing position includes according to whether we want to display a front, back, side, top or the bottom viewing of the scene. We would also pick a position in the middle of the group of objects or even inside a single object such as a building or a molecule. Three-dimensional viewing pipeline consisting of mainly five stages: modeling transformation, viewing transformation, projection transformation, clipping, and viewport transformation. Both the two-dimensional and three-dimensional pipeline are very similar. Three-dimensional viewing transformation pipeline refers to the series of transformation applied to the 3D objects in order to convert them from their object space coordinates to the final coordinates in the viewing space. This pipeline involves several stages. It includes a modeling transformation, viewing transformation, projection transformation, and viewport transformation. Now let us see what are the main stages in two-dimensional viewing port transformation pipeline. Basically, it consisting of viewing transformation, clipping, projection transformation, viewport transformation. Modeling transformation. The modeling transformation is the first step in the pipeline and involves transferring the vertices of the 3D object from their local coordinate system, where it is known as object space, to the common word coordinate system to the word space. This transformation it includes the operations like translation, rotation, and scaling to the position and orient the object within the word. Second one, weaving transformation. The weaving transformation is also known as the camera transformation or the eye transformation, where it defines the position and the orientation of the virtual camera or the viewer in the screen. It transfers the coordinates from word space to the normalized viewing coordinate system, where the camera is located at the original looking down the negative z axis. This transformation allows us to define what position of the 3D scene will be visible from the camera's viewpoint. Third one, clipping. Clipping are the techniques used to optimize the process by discarding the objects or the position of the objects that are outside the view of frustum or which are not visible to the users. Clipping removes the parts of objects that are outside the view of frustum, where the objects or the faces that are not facing to the viewer by the other objects. Projection transformation. Projection transformation maps the 3D scene onto the 2D viewing plane. It stimulates the perspective effect and accounts for the foreshortening that occurs while projecting a 3D scene onto 2D surface. The transformation can be done using the different projection techniques such as perspective projection or orthographic projection. Viewport transformation. Viewport transformation maps the normalized device coordinates from the previous stage to the actual scene or the viewport coordinates. It involves scaling and translating the coordinates to fit within the boundaries of the screen or window where the final image will be displayed. Now, RGB color model. RGB stands for red, green, blue, and they are the primary colors of white light. The RGB color model is an additive color model. RGB color model is widely used for color representation system in computer graphics and visualization. It is an additive color model in which colors are created by combining a red, green and blue light in various intensities. The RGB model is based on the principle that when a red, green and blue light are mixed together at full intensity, they produce white light, while the absence of all three colors results in black. In the RGB color model, each color models R, G and B is typically represented by a 8-bit value ranging from 0 to 255, providing 256 possible intensity levels for each component. By varying the intensity levels of red, green and blue, a wide range of colors can be achieved. For example, pure red is represented as 255, 0, 0. Pure green as 0, 255, 0, where 255 represents the green color, and pure blue as 0, 0 and 255, where 255 represents a blue color. In this, a 255 represents a green color, and in this, a 255 represents a pure red color. CMY color model. In computer graphics and visualization, the CMY color models, also known as the subtractive color model, is an alternative color representation system to the RGB model. CMY stands for cyan, magenta and yellow, which are primary colors in this model. The CMY model is based on the principle by subtracting the different amounts of CMY pigments from the white light, various colors can be obtained. In the CMY model, each color component CMY is typically represented by an intensity value ranging from 0 to 1 or a percentage value ranging from 0% to the 100%. A value of 0 represents the absence of the color component. A value of 1 or 100% represents the full intensity. By varying the intensity levels of CMY color, a wide range of colors can be obtained. Thank you.